During this, just let me know. And I was just going to go through the PowerPoint basically, and just kind of further talk about stuff like that. And then for the two math problems that are at the end, we can do them in more detail because there's no detail on how to solve them in the PowerPoint. You guys will be fine. They're really, really easy, but let's do that. Share. All right, so you guys see the PowerPoint on the screen now, I believe.
Yeah.
All right, so this whole section takes Ohm's law and applies it to a circuit. So basically what a circuit is in its simplest form, if you think of it like that. So as we said before, anything that has voltage has potential difference, like a battery, and it can do work, but we know that if it's not hooked up to anything, it won't do any work. Like in a perfect world, batteries don't die unless they're being attached to something. We know that they really do, but that's not really the point now. So anything that has voltage can do work, but unless it's hooked up to something, it won't do anything. So in a circuit, we take that voltage source and something.
Don't do it, Dad.
Okay. And some sort of device, and then we have to connect the two things with some sort of items, usually wires. So the simplest circuit is a voltage source, a device that we're going to power, and then material, think of it, wires to connect the two things together. Right? As easy as that. Circuits are, we think about on and off. Well, instead of being on or off, in circuits, we talk about open or closed. And think of it, a circuit as a bridge, right? So in order for the cars to get from one end of a bridge to the other, the bridge has to be closed or lowered. The lanes have to meet. That's the same thing. So in a closed circuit, the circuit forms a loop. Basically, it starts where it ends. And this way, the current, the electric current, can run through it, and it's able to get back to the beginning again. You can think of a closed circuit as like the lazy river. All right, as long as there's no breaks in the river's always going to flow, and if you are an electron, you will be taken through the entire lazy river. That's a closed circuit. Right. The opposite would be if we take the circuit and we open it. Again, think of a bridge. If a bridge is open, right, there is some break in the pathway. And in this case, the current stops flowing. So the simplest thing to think about would be a light switch. If the lights are on, the circuit is closed. When the light switch is turned on, it connects the circuit together. It closes the loop. And if the circuit is open, that's when you turn the lights off. When you turn the lights off, the circuit breaks and there is an opening in it. So the pathway is not complete, and therefore the lights turn off. Right. So another thing to look at is this. Let me I have this clip here that I want to show you guys. I know. All right. Okay, so do we see a kid on an electric fence?
Yeah.
All right. Yeah. Okay, so this is from Jurassic Park. And is it playing now?
Yeah.
Okay. All right. So pay attention to what the guy with the white hair says. Right. Okay, so he's going to say something else, and then pay attention to the screen itself. All right, so I don't know if you can see right now, but there's a green button, and above the green button, the word, it's very blurred right now. It says open. There we go. And then she pushes it. So when she closes the circuit, she basically is turning the power back on in the park. So that's, a big extravagant way of doing it. the circuit was open, there's no power in Jurassic Park, right? And then she closes the circuit and then the power turns back on. And then there's one more part to kind of take a look at. Can we play this up here now? Second one. All right, so she's basically closing each individual circuit. All right. All right, so then she'll get there. And then he flies off. Yay. The last question. So she turns on each individual part of the park with that big board. What do you think that's like in your house?
Circuit breaker.
Yeah, there's a big circuit breaker. Basically, that's what he's doing. He or she is turning on each individual circuit breaker for the entire park. So she first had to pump up the charge, right? Then she closes it. That starts the individual parks, like the things turning on, and then she has to turn on each part individually. And all right. Okay, so does anyone have any questions about what to fill out for those questions with the movie? Okay, so let's go back and look at the PowerPoint. All right, so components of a circuit. So the basic components that everything needs is a power source, again, a battery, a power supply. If it's drawn out in a diagram, it gets the symbol to the right. It's basically two lines, and they're different in length to show there is a difference or a potential difference. You need a resistor because that's your device. And resistors are drawn out in circuits as lines with a bunch of spikes in them, as if the current has to bump all around that. So that's a resistor. And then the most common resistor that we'll use in this class is a light bulb. And a light bulb is basically a resistor. And in this case, the resistor just glows when it has current running through it. All right. Okay. So circuits can come in two forms, series and parallel. All right, so in a series circuit, think S for single, one pathway. So everything's wired together in one distinct pathway. Because of that, every device in a series circuit has the same current running through it. But each resistor would have a different voltage applied to it. So again, I think the easiest way to think about it is to think of electric current as water flowing, bless you, buddy, through a river. So because there's only one pathway, the flow of water can only go at one speed. That's the current. You can't have multiple different speeds of current running through this single stream. If a series circuit is broken at any point, the entire circuit is incomplete because it becomes open. I know a lot of you guys are muted, and that's fine, but you can still just shout out if you know this. If you ever had to deal with Christmas lights, where one Christmas light goes out and all of the bulbs go out, that's a series circuit. As soon as one thing breaks, it opens up the entire circuit. Okay, so that's a series circuit. And to find the total resistance.
Sorry.
Oh, yes.
Sorry. Would like replacing the light bulb then be like closing the circuit again?
Yep. So if you replace that one bulb, you have replaced that one break. You basically reclose the circuit and it all works again. Yep. But that's why if you have one of those old branches, like you have to test like every single bulb, because any one of the bulbs that's out, the whole thing is off.
Then how come it still works when like some of them are out?
So what they do nowadays is that they will wire, like, let's say it's like blue, green, and red. Maybe they put all the blues on one series, all the greens on a series, and all the reds on a series. So if the blue bulbs go out, the green and reds will still work. Or they wire them in a way where it's like a series circuit and it's patchwork together with a bunch of other circuits. So that way, if only one goes out, it doesn't shut the whole thing off. The more circuits and pathways there are, the more expensive the lights are, but the less likely you have to replace every bulb if something goes wrong. So it's a good give and take. Most circuits nowadays don't have this set up because it's such a pain, because if one thing goes out, the whole thing turns off. All right. So again, since there's only one pathway to take, the current has to be the same. And then to find the total resistance of all of the resistors, you just add them together. So the formula is R total is R1 plus R2 plus R3 and so on and so forth. It just wouldn't end. So let's try, oh, okay. One more thing. Because our resistors are always whole numbers, the total resistance is always greater than the individual resistors in a series circuit. Okay, so the total has to always be greater than the individual resistors in a series circuit. No exceptions to that rule. All right, so here's a picture of a series circuit. So we have a light bulb, or sorry, we have a battery, we have a switch, and we have 3 lights. And if we kind of trace the black line from the positive terminal of the battery, we go over the switch, we go through each light bulb, and then we come back again to the bottom, the negative part of the battery. It's a complete circuit, right? There's no breaks in it, so the circuit is closed and it will run. And then basically here's what we have. We have 3 2-ohm light bulbs are hooked up to a 12-volt source in series. What is the equivalent resistance or total resistance? And what is the current in the circuit, right? So let's show you how we do this. So I know here are the answers, but I'll do it like this. New share, and we'll share. Okay, so apologize for my terrible penmanship. All right, so to find the total resistance, we're just going to add together the 3 resistors, which is 2, 2, and 2, which would give you
6.
6. Oh my goodness. And it's resistors, so we get ohms, right? And then to find the current, it's V equals IR, right? So we know the voltage is 12. We're looking for I, and the resistance is 6. All right, so to get rid of that 6, we divide both sides, and we get I is 12 divided by 6 would be
2.
2, and the unit for current is amps. There you go. That's a series circuit problem. Okay. Notice we can't find the current for each individual item because they all have the same current. So every device in that circuit has 2 amps of current running through it. Let me know if I can erase this or if you need some more time seeing this.
You're good.
All right. Everybody else good? All right, so clear that, and then we're gonna go back to our PowerPoint. Here we go. All right, so then parallel circuit. So in a parallel circuit, the devices are connected, so there's more than one pathway. We usually draw them and we make parallel lines, so that's why they call them a parallel circuit. Because there's more than one closed pathway to take, if the current finds a break in a circuit, it's open in one part, it will still flow through the other parts that are closed. So if we look at this picture that just popped up, if you follow the line from the top part of the battery, the larger horizontal line, it goes up, the current flows in, and then we have this three-way street basically. The current can flow through the top, which is labeled 1, it can flow through the middle, which is labeled 2, or it can flow through the bottom, which is labeled 3, right? Each of those pathways are unique in their own way. And if you are to break any one of them individually, the other two would still work. So if you opened up R2, right, instead of the current being able to go straight through, the current would have to go up through I1 or would go down through this I3 branch, but it still can travel through the entire circuit. So again, in a parallel circuit, if one branch is broken, the other branches will still work.
So like in a parallel circuit, then the current itself cannot be divided into 3. It has to go through one at a time.
It actually, so think of, again, to go back to the water analogy, think of it like this. The water is at the top of a waterfall, and it's got 3 different ways to get down. It can go down any one it wants to. So some of the current will go down I1, some will go through I2, and some will go through I3. It's not going to ignore one branch altogether, unless, and this would not come up in this class, unless one of the branches was so restrictive that you basically didn't let current go through it. But that wouldn't show up in anything you guys would see. So if there are 3 branches available, the current's going to go through all 3 branches. It just will go through each branch at a different rate. Does that answer your question there, Joy?
Yeah, it does. Sorry, yeah.
Oh, no problem. Okay. So because current has a decision to take, and it's going to basically take it based on the resistance. So in a parallel circuit, the current is different in each pathway, but the voltage across the circuit is the same in each path. So if you go back and look at that other picture from the previous page, all right, the current's broken down to I1, I2, and I3. Each of those 3 have a different current. I1's current is different than I2, I2's is different than I3. However, the voltage across I1, across I2, and across I3 are the same. That is the difference between parallel and series, or one of the differences. Okay? In a parallel circuit, voltage is the same, current is different. In a series circuit, the current is the same across all the resistors, but the voltage can be different. The formula to find total resistance in a parallel circuit is a little more complicated. It is 1 over R total equals 1 over R1 plus 1 over R2, and then so on and so on and so on. So a little more complicated than a series circuit. So again, so if we look here, this is a parallel picture off to our right. Again, if you follow the red line from the battery, the current flows down, and then it can either go through the first light bulb, or it can travel and go through the second light bulb, or it can keep traveling and go through the third light bulb. Because it has three options, that's a parallel circuit. Also, if we got rid of any one of these three light bulbs, the other two light bulbs would still work because each unique branch is its own thing. It doesn't matter what anything else happens to like the other three branches. All right. So if we take a look at this one, there are three questions. Find the current in one branch, find the total resistance, and then find the current across the battery. Right, so that is what we are going to do. Oh. So I'm going to break up that whiteboard in a second again, and then we'll take a look how to do this. All right. So to find the current in one branch, that's just V equals IR. And since all the resistors are the same, we only have to do this once. So we know the total voltage is 9. All right, I is what we're looking for, and R is 3. We divide both sides by 3, and I would be what?
3.
3 amps. Okay, so that's part 1, easy peasy. All right, part 2, we'll change up the color here too. All right, to find the total resistance, so that's 1 over R total equals 1 over R1, which is 3, plus 1 over R2, which is 3, plus 1 over R3. So we get that. And 1/3 plus 1/3 plus 1/3 is 1. 1. All right, so here's the part that gets a little confusing. So what we have found out is that 1 equals not R total, but 1 over R total. So we technically have to flip this over. So if we flip this upside down, we just get RT. And technically, we have to flip the 1 upside down. So we would take R number 1, that would go on the bottom. And then what number do you put up top if you flip something upside down? If you take the inverse of something, what number would go on top of a fraction?
The denominator?
Right, and the denominator of any number that's a whole number is the number 1. So in this particular problem, the inverse of 1 happens to also be 1. After this problem, I'll show you an example where it doesn't work out as easily, just to kind of show you the difference there. So now the last part is if we know the total resistance, which is 1 ohm, we still know the voltage, which is 9, right? We can find the current across the entire circuit or across the battery, and that's going to be 9 equals I times 1, and therefore the current across the whole thing is 9 amps. And that's a parallel circuit. Does anybody have any questions about this particular problem? I'm going to do one more just to show you an example of one that doesn't work out as easily. And then that's it. That's the end of today's lesson. Any questions?
Nope.
All right. All right, so let's just try one more real quick. We'll just make one up. So let's just say we had this. All right. V is 12. All right, and we have 2 resistors, and their values, here, R1 is 2 ohms, and R2 is 4 ohms. Okay, so if we wanted to find out what is the current across the whole circuit, we would first have to find out R total. So it'd be 1 over R total, and that's going to be 1 over 2 plus 1 over 4. All right, so if you forget, you can't add these together as is. You have to find the least common denominator, which would be 4. This becomes 2 over 4. When you add them together, you get 3/4 equals 1 over RT. Okay. But I cannot use 1 over RT in my problem. I have to use RT. So if I flip RT over, I get the total resistance equals not 3 over 4, but 4 over 3, which is 1.33 forever. And then once I know R total, I could go back and using my voltage, I could find I, and I could write to find the current across the battery. The voltage equals 12 times I times 1.33. All right, and then if we solve for I, we would end up with 9.02 amps, or basically you could say 9 amps. All right. That's what happens if it's not like a perfectly whole number. So that is the notes on Ohm's law. Does anybody have any questions on anything?
Convert it into decimal?
Say again?
Do you have to convert like the
No,
total?
you can leave it as just 4 over 3 and plug it in that way. It'd be fine. Whatever way you're more comfortable with, doesn't bother me. I know some people hate fractions, so I'm gonna give you that option. Anything else, guys?
Nope,
All
all good.
right. Well, it's been good seeing you guys. Stay safe. And if you have any questions, let me know, all right?
Have a nice day, Phil.
You too. See you guys
See you,
later.
Pam. Stay safe.
Bye.
Bye.
Bye.